let's just have a short review of what we took up last time. So for the BJT, we have various operating modes. Okay, and the way we identify the operating mode of the BJT is by taking a look at the collector-based junction and the emitter-based junction. Okay, so if I take a look at the emitter-based junction, that can either be forward biased or reverse biased, and also the collector-based junction. So that can either be forward biased or reverse biased. So we actually have 4 possible combinations, and we discussed this last time. No? So these are our 4 possible combinations. Okay, so let's see. No? What is the operating mode when the emitter-based junction is forward biased and the collector-based junction is reverse biased? In other words, dito. No? What is the operating mode? Just shout it out, no? If you know the answer. Ano yung operating mode dito? Anyone?
Saturated po.
Emitter base is forward biased and the collector base
Active.
is... Yeah, that's right, no? So,
Okay.
pag yung emitter base is forward biased and the collector base is reverse biased, this is the active mode. And in the active mode, what is the relationship between your base current and your collector current? You remember? Anyway, sa active mode, ang characteristic ng active mode is IC is equal to beta times IB. That is in the active mode. Remember, that relationship only holds true in the active mode. Okay. Dito naman, ano itong mode na to? Pag parehong forward biased. Shout out.
Saturated po.
Yeah, that's right, no? This is saturated. And when it is saturated, ano yung characteristic nun? Your VCE is equal to VCE SAT, which is approximately equal to 0.2 volts for silicon. That is the primary characteristic of a transistor that is saturated. VCE is equal to VCE SAT, which is 0.02 volts for silicon. Kapag parehong reverse biased, ano yung tawag dito?
Sir, cut off.
That's cut off. Yeah, this is cut off. And here, IB equal to IC equal to IE is equal to 0. Okay. And then itong last quadrant natin, no, this is what you call reverse active. Excuse me. Sorry about that, no? So dito sa quadrant na to, when the emitter-based junction is reverse bias and the collector-based junction is forward bias, you call this reverse active. And this is this is not normally used. Not normally used. So nabanggit ko last time na oftentimes when you find your transistor in the reverse active mode, it's because somebody connected it the wrong way. Because the emitter and the collector are not perfectly symmetrical. So that the transistor performs better when the emitter is really the emitter than if you mistakenly made the collector the emitter. So those are your four operating modes. Okay. And then we had this exercise where, okay, I gave you this particular transistor. No, the transistor parameters are VCE sat 0.2, VBE active 0.7, beta equal to 100. These are your transistor parameters. So ito napipick up yan sa datasheet ng transistor. And then these are circuit parameters. VCC 5, RC1K, RB is 10K. And then I told you, okay, first determine IC sat. IC sat in this case is 4.8 MA. And then for these values of input, what are the values of your output? No? So we went through that, okay? Because the voltage is, the input voltage is less than 0.7, you get no conduction, it is cut off, and therefore your output is 5 volts. No? Your transistor will only start getting out of cutoff, will start going into active mode when your input voltage becomes 0.7, because that's the only time for this particular circuit. If your input voltage is 0.7, that's the only time you forward bias the base emitter diode and get a base current that is flowing. So here, I wrote it is on the verge of becoming active, but your output is still equal to 5 volts. Now here, when your input voltage reaches 1.18 volts, it's not shown here, but your collector current is already actually 4.8 MA. So it is on the verge of being saturated, and your output now is VCE sat. So this is VCE sat. And anything higher than 1.18 volts, your output will be equal to VCE sat. So I said, okay, so you can see that anywhere from 0.7 to 1.18, you are in active mode. And when your input is 0.7, your output is 5. When your input is 1.18, your output is 0.2. So if you had a signal, that actually varies from a maximum of 1.18 to a minimum of 0.7, such as this signal, okay, you expect your output to vary from a minimum of 0.2 to a maximum of 5. And notice that here there is amplification. So this is how this transistor behaves as an amplifier. But it will only behave as an amplifier, or it will only behave linearly if your input is within this range. Okay. If we extend the input beyond that range, for example, from 0 to 1.5, and I showed this last time, okay. Beyond that range, whenever the input exceeds 1.18, dito, no? At this point, your input is exceeding 1.18, your output will already clip to 0.2 or VCE sat. And whenever the input goes below 0.7, your output will already clip to 5, because here it is cut off. No? So this area, it is cut off, and this entire area, it is saturated. While we would want our output to look this way, this is what we want our output to look like. Unfortunately, it does not look that way because our input range was too large. And this is what you call distortion. And I started to point out that itong value na to, no, let me go to this. No, this value 0.94 volts, which is the middle of my signal. So this is my input signal. Itong 0.94 volts is very important. No, in other words, my signal varies by peak to peak. This is 0.48 volts. 1.18, 0.7, that is 0.48. So my input signal is a 0.48 volt peak to peak signal. If I raise it so that the middle is beyond 0.94, I'm going to cause it to saturate faster. Okay? So magkakaroon ako ng distortion dito sa baba. That's what's going to happen if I raise this value 0.94, no? So itong value na 0.94 is very important. Actually, we can consider our input to be the sum of two quantities, no? This is my input, V in. It's the sum of my actual signal that I want to amplify and a DC quantity. So imagine it this way. This is my input. This is the signal I want to amplify. It has a peak-to-peak value of 0.48. No? So it goes from plus 0.24 to minus 0.24. And I'm adding a DC value, which is 0.94. If I add this to this is what I'm going to get. And this DC value is very important. Itong value to, this is very important. No? This is what you call the bias of your input. If you do not set this value properly, your amplifier, you will not be able to optimize the operation of your amplifier. Now this is beyond the scope of this course. No, we're not really going to discuss transistor biasing. I just wanted to give you an idea of what transistor biasing was all about. No? It's properly setting up this DC value so that you get the maximum possible output voltage swing of your linear output voltage swing of your amplifier. And I also want to mention that in actual practical circuits, we don't actually use a separate power supply. We actually have a resistor network connected to VCC. That is what generates this bias. Okay, so I'm not going to discuss that any further. That's going to be taken up in EEE131. But maybe I ought to mention that in previous offerings of 123, we actually discussed biasing. Kaya sa notes that I passed on to you last time, nandun pa yung notes ko on biasing. No? But I noticed that this was taken out of the material probably because we have a compressed semester. So kukunin na lang nyo yung biasing in EEE131. Okay. Are there any questions? So I'm not going to touch on biasing anymore. Any questions? Okay, so what I'm going to do from this point onward, I'm just going to supplement the material that was already posted by Dr. Sison in UVLE in his study guide for this module. So first, let's just take up some very useful transistor current relationships. Okay, this is an NPN transistor. So far, we've limited our discussion to NPN, but like I said, for a PNP, it's the same principle, except that the current directions are opposite. So I said that this follows Kirchhoff's current law. In other words, the current entering the transistor must equal to the current leaving the transistor. So this is the application of Kirchhoff's current law to the transistor. IE, the current leaving, is equal to IB plus IC. Both of these are entering. If we assume that the transistor is in active mode, then IC is equal to beta IB. Remember that that is only true in active mode. Okay. If I wanted to get a relationship between, okay, so this is a relationship between IC and IB. If I want to get a relationship between IE and IB, what is that? Well, IE is IE here, is IB plus IC. Okay. But what is IC? IC is beta IB, no? So this is IB plus beta IB. So this is just 1 plus beta times IB. So this gives me a relationship between IE and IB. IE is 1 plus beta times IB. No? So the reverse relationship, IB is IE over 1 plus beta. Okay, on the other hand, I can also rewrite this as follows, no? Itong equation na to, I can write this as, okay, this is IC plus IC over beta. IB plus IC is equal to IC plus IC over beta. So this is IC and this is IB. So what is this? This is IC, okay, 1 plus 1 over beta, okay, or IC times 1 plus beta over beta. So I get this relationship. IE is equal to IC 1 plus beta over beta. Or the reverse relationship is IC is equal to IE times beta over 1 plus beta. Okay, you don't really have to memorize this, no? You don't have to memorize it because if you know that IC is beta IB and you know this KCL equation, you can derive any of this. Okay, but sometimes it comes in very handy that you know this. Okay, in the relationship between IE and IC, you just always remember that IE should be greater than IC. IE should be greater than IC. No? And therefore, you have to multiply IC by a number that is greater than 1, no, to get IE. Okay, another thing that I want to point out is if beta is very much greater than 1, then 1 plus beta over beta is approximately equal to 1. Okay. So when beta is large, when beta is very large, IE is approximately equal to IC. Now, sometimes we're just trying to make approximations. We're just trying to get a feel for the operation of the circuit. Now, if you don't want really, if you don't need really a very exact calculation, then you can just say that IE is approximately equal to IC. No? Because ito, remember this is small. No? Ito maliit na maliit. So kung maliit ito, yung current na nanggagaling dito, bababa lang baba dito. No? Okay, so it's IC is approximately equal to IE. Okay, are there any questions? Any questions? Okay, so I'll supplement now what Dr. Season discussed in his pre-recorded lectures, no? So, yung model natin ng transistor in the active mode, what is the model of our transistor? Between the base and emitter, we have a diode. So let's say this is my emitter, this is my base. Between the base and emitter, I have a diode. And between my collector, so this is my collector, and emitter, I have a controlled source, and this is beta times IB, where IB is the base current. So this is my model. Okay. In other words, I can use the transistor to establish the value of a current that is flowing through a load. So, sorry, can use transistor to establish a current flowing through a load. Okay. And what will my circuit look like? Well, the simplest circuit, which we already discussed quite at length, no, last time, is something's wrong with my is yung ano, no, yung circuit natin na ganito, no, where this is my load. So I VCC, this is my load, RB, VI. No? Okay, what is IB? IB, we already said, was VN minus VBE, this is VBE, divided by RB. No? What is the value of VBE? Can somebody shout it out to me? Assuming this is a silicon transistor.
Sir, 0.7.
That's right, no? So IB will be VN minus 0.7 over RB. Okay, and IC will just be equal to beta IB. So this is beta multiplied by VN minus 0.7 over RB. So if I want to establish a particular current through a load, okay, all I have to do is select RB. Okay, so beta is a transistor parameter. Okay, select RB so that that current is the one that flows through the load. No, so it's just a matter of, okay, if, for example, no, if IL is the desired current, is the desired load current, then what is RB? No, let's say IL. No, this is the load current that we want. IL, that is the desired load current. Then what is RB? Okay, RB will just be equal to. Let me do this right. No, RB will just be equal to what is this? Beta over IL multiplied by, tama ba? Sandali. Yeah, multiplied by Vn minus 0.7. Okay? So ito lang, no? Okay, and then you just have to check, just need to check that it is in active region, no? No? After computing for RB, you just need to check that it is in active region. And how do you know that it is in active region? If VCE should be greater than VCE SAT, no? You have to check that VCE is greater than VCE SAT. Because if VCE is less than VCE SAT, then you know that it is no longer in the active region, it is already in saturation. And your formula, beta IB, is no longer valid. In other words, this is no longer the correct model for your transistor. Okay. So given a desired load current, you just use this formula. Now, what's wrong with this circuit, or what is the disadvantage of this particular circuit? Or a weakness, no? Weakness. The weakness of the previous circuit Okay. The weakness of the previous circuit is RB very much dependent. Your computed RB, no? Computed RB is very much dependent on beta. If you take a look here, okay, itong betang to, yung value ng RB natin is very much dependent on beta. Is that good or bad? Well, actually, it's not good. No, it's not good. Why? Sorry. Why? No, beta varies with temperature. Beta also varies from transistor to transistor even if they are the same part number. Even if they are the same part number. No? I'll give you an example. You have a transistor, the part number is 9013, no? FCS 9013 transistor. Okay. The beta typical is equal to, if I'm not mistaken, 90. But if you take a look at the data sheet, the minimum beta, I think, is 60, and the maximum beta is, if I'm not mistaken, something like 200. No? So anyway, this is just an example, no? Possible example. In other words, it's the same part, it's the same transistor, and yet the range of beta is very large. So kung ganito kalaki yung differences in beta for the same transistor, okay, granted, no, I get the correct load current. So let's say this load is sensitive to current. I have to set it to the correct load current. Let's say masira yung transistor, I replace it with a new transistor. That transistor has a different beta. Mag-iiba ngayon yung load current ko. So this particular circuit, we say, is very sensitive to the value of beta. Okay, so what is the solution? Sorry. Okay, you add a stabilizing emitter resistor. You add a stabilizing emitter resistor. So what will my circuit look like? Okay, this is my load, VCC. Kanina sa circuit ko, the emitter was connected to ground. Now here, I put a resistance. I'll call this RE. Okay. Now, I can actually get rid of my base resistance. I can just apply my input directly to the base. No? In the earlier circuit, I needed the base resistance because I cannot put a voltage directly across the base emitter. No? The base emitter has a forward voltage of 0.7. If I put a voltage greater than 0.7, I'm going to burn the transistor. No? It's going to be like an invalid circuit. For example, if I put a voltage of 5 volts across my base emitter, 0.7 lang yung equivalent circuit niya, it's like an invalid circuit. Ang mangyayari in real life, masusunog yung transistor natin because there's nothing that limits the current flowing into the base. No? But if you put an emitter resistor like this, then I can now apply my input directly to the base. So how does this work? No? So again, no, if we assume active operation, assume active mode, what is my equivalent circuit? Your equivalent circuit is I have V in, then I have my diode here, I have my emitter resistor RE, okay. So this is beta IB, this is IB, and this is BCC. Okay, so this is my equivalent circuit. Okay, assuming active mode. Okay, so this is my collector. No, this is my collector, and this is my emitter. No? I just wanted to extend that. Assuming active mode, what is the value of VE? Can anyone tell me? What is the value of VE? In terms of V in, I have a voltage here V in. What is going to be the value of VE?
Is that a silicon diode po?
Yes, it's a silicon transistor.
Okay, so V in minus 0.7.
Yes, that's right. No, so VE is just going to be V in minus 0.7. So what is IE? IE is just going to be VE over RE. No? So this is V in minus 0.7 divided by RE. Now, what is IE in terms of IC? What is IE in terms of IC? You recall yung relationship natin, 1 plus beta over beta? No? You recall that relationship? Remember that IE is always larger than IC. No? So you should multiply IC by a number that is greater than 1. So this is a number greater than 1 to get IE. Right? So V in minus 0.7 over RE, okay, is what? Is equal to IC times 1 plus beta over beta. Sorry, no, I forgot to put the load. May load nga pala tayo. Nakalimutan ko ilagay dun sa circuit natin yung load. No? Okay. Let's put the load. So I have a load. I have a load here. And then this is VCC. So this is IC. No? IC is also equal to my load current. No? IC is I load. That's my load current. Okay, but recall that if beta is large, okay, 1 plus beta over beta is approximately equal to 1. And therefore, IC is just approximately equal now to V in minus 0.7 over RE. No? Notice, I established my load current. So this is my load current is not a function of beta. This IC is not a function of beta. So anong ibig sabihin nun, no? Kung masira itong transistor na to, palitan ko ng ibang transistor, kahit na mas mataas yung beta o kahit na mas mababa yung beta, basta't malaki yung beta, as long as this relationship holds true, then my load current will be the same. And that's why it's a better current source. Okay. So, did you see that? I hope that you saw that. No? Dito sa previous example natin, no? This is IC, no? This is my load current. It very much relies on beta. Okay? So magbago yung beta, magbabago yung IC ko, no? But here, IC hardly is a function of beta. Meron pa rin, ano? Kasi 1 plus beta over beta. But that's very close to 1. So my I sub C in this case is quite stable. Okay, but remember, no? Remember, you always have to do the check to see whether it is saturated or not. So let's put some actual numbers. Let's put some actual numbers just so we can illustrate the process. So let's take an example. Okay, in my example, so ganun, ano? Is my load, let's say RL is equal to, and these are just numbers that I'm putting in, ano? And let's say, let's say RE is also equal to 100. And let's assume that beta is equal to 100. Okay, so this is Vin. And VCC is equal to 5 volts. Okay. So the question is, what is the load current when Vin is equal to, let's say, 2.7 volts? What is the load current when Vin is equal to 2.7 volts? Okay. So what will VE be equal to? Sigaw na lang ninyo, what is VE? If Vin is 2.7 volts, assuming that it is in active mode.
2.
2 volts, ano? Therefore, what is IE? IE will be just 2 volts over 100 ohms. V is the voltage here. So divided by 100, that is equal to IE. Ito yung IE. Okay. So what is this? This is 0.02 MA. Sorry. No, not MA. No, 0.02 amperes. 20 MA. .02 amperes or 20 MA. 20 MA. Okay, what will be the load current? IL is equal to IC, okay, which is equal to IE times 1 plus beta over baliktad, no? Beta over 1 plus beta, sorry. Okay, IL, your load current, this is your load current, is equal to IC, no? Which is equal to IE times beta over 1 plus beta. Again, no? The way you remember the relationship, ano yung mas malaki, IE or IC? What is larger, IE or IC? IE is always larger than IC. Yeah, IE is always larger than IC, no? Because IE is IB plus IC. So if you want to remember ano yung tama, is it 1 plus beta over beta or is it beta over 1 plus beta? tandaan lang ninyo ano yung dapat mas malaki, no? So IC is smaller, so you should multiply IE by a number that is less than 1, no? So if I do this, I'm going to get IL is 19.8 MA. Okay, IIL is 19.8 MA. Okay, what is the value of VC? So this is C. What is VC? You just do a partial KVL here, you know, an incremental KVL here, right? 5 volts minus VC is equal to RIL times 100. Or VC is 5 volts minus IL times 100. Okay, and if I do that, IL is 19.8 MA or 0.0198, well, 19.8 times 0.1, so that's 1.98. 5 minus 1.98, I'm going to get 3.02. No? Tama ba? Yeah. Yeah. I'm going to get 3.02 volts. I do not trust my arithmetic anymore. No, let me just check. Yeah, I should have trusted my arithmetic. Okay, how do I know that this is in active mode? So you have to check. And how do I do that? I compute for VCE. Okay, what is VCE? VCE is equal to VC minus VE. So that's equal to 3.02 minus, ano yung VE natin? 2 volts, no? Minus 2, which is equal to 1.02. Notice VCE is greater than VCE SAT. No? If this is silicon, ano yung VCE SAT? I just want to know if you remember.
0.2?
0.2, sir.
0.2, right? So VCE is greater than VCE SAT. So alam ko ngayon na hindi ito saturated. Kung hindi ito saturated, ibig sabihin valid yung assumption ko kanina na IC is equal to beta times IV, no? And all of these equations now are valid. Itong mga equation na to, ito, pwede mo lang gamitin ito pag active mode, no? Itong IC is equal to IE beta over 1 plus beta. You can only use that if it is in the active mode. It is not in saturation or not in cutoff. Okay, so that means okay, no? So here, ibig sabihin yan, okay. Okay, what if nawalan ako ng space, no? What if RL was equal to 1,000 ohms? So parang what if RL is equal to 1,000 ohms? Ano magiging value ng V of C?
.2 po?
No, not exactly. No, if this is your check, ano? What if RL is equal to 1,000 ohms? If I follow this formula, if you follow the formula, you have VC is equal to 5 minus IL times 1,000. What am I going to get? IL is 19.8 MA, no, times 1K. So this quantity is going to be 19.8 volts. So I'm going to get 5 minus 19.8, no? I'm going to get minus 14.8 volts. Okay? Pag nakita niyo yung negative yung voltage dito, magduda na kayo. Because I don't have any negative supply anywhere here. No? So, seeing that this is negative, question mark na yan. No? Question mark na yan. Dapat wala tayong mga negative voltages dito sa circuit natin. No? Anyway, if you compute for VCE, so let's just go through the motion. Ano? If you compute for VCE, VCE will be minus 14.8 minus VE, which is 2. I'm going to get minus 16.8, which is less than VCE SAT. No? Meaning to say, if I had chosen a load resistor equal to 1,000, no? if this is 1,000, if RL is equal to 1,000, then with my input equal to 2.7, no, transistor will saturate. So, question is this. Ano yung magiging tunay na value ng IL? So, if RL is equal to 1,000, Vin is equal to 2.7, what is IL? What is IL? Okay. So how do I compute for IL? What is this? This is 100. This is 1,000. And this is 5 volts. No? This is Vin, which is equal to 2.7. Okay. Anyone? What is going to be the value of IL? Somebody says 3 MA. Nice try, no? It's a good try. But I think it's not right. 2.3. Okay, let's check, ano? So anong value ng VE? What is VE? This diode is still forward biased, no? Even in saturation, this is still forward biased. So what is VE? VE will still be equal to 2 volts. What will be the value of VCE? VCE will be VCE SAT, which is equal to 0.2 volts. And therefore, what is the value of VC? VC will just be VE plus VCE. It's a partial KVL, no? Differential KVL here. The voltage at VC is VCE plus VE. So this is 2.2 volts. And therefore, what is IL? IL will just be 5 minus 2.2 over 1,000. Okay. Okay, which is just 2.8 MA. Very much smaller than our intended load current of 19.8, no? 19.8 MA. This was our intended load current. So yeah, no, I just wanted to illustrate the nuances of the transistor. So you always have to do your check. You always have to do your check whether the transistor is really in the active region or not. Um, Actually, itong circuit na to, this is a popular current source, no? Current source circuit. No? Let me redraw it. You have V in, okay, and then you have RE, and then your load, and then you VCC. No? This is a popular current source circuit. V in and RE establish IL. So this is IL. V in and RE establish IL. Okay. And as long as you can ensure, that even with changing load, hindi magsasaturate itong transistor na to, okay, then this IL will always remain constant kahit na pabago-bago yung load. No? Now, how can you ensure that? One way of doing that is by making VCC very large. If VCC is very large, then it will take a longer time for your transistor to saturate. No? If you take a look at your LED lights, yung iba sa inyo, no, yung mga ilaw sa mga bahay ninyo, no, mga LED na, tapos pag binuksan nyo, madaming LED. Actually, ganito lang yung circuit sa loob nun eh. No? That's what they call the LED driver. No? You just have VCC, and then you have your LEDs. Okay. And then you have your transistor, and then you have RE, no? And V in. Usually you choose V in and RE. So IL, ito yung IL. For yung mga LED lights, let's say yung mga 1 watt LED lights, IL is approximately equal to 300 mA. No? And itong VCC, mataas yung VCC na to, no? Because this is gotten from your 220 volts. Sometimes they rectify your 220 volts directly. So this VCC is very large. So kahit na ilang LED ang ilagay mo dito, your current will stay at 300 mA. So sometimes you have just one LED. Sometimes you have, well, one LED is a little bit too few, no? But sometimes you have 10 LEDs. Sometimes you have 20 LEDs. Kahit na gaano kadaming LED rito, the current flowing through your LEDs will always be the same because that is established by V in and RE. So anyway, that's just something on the side, no? That might interest you. On the other hand, it also might bore you. So sorry for that. Okay. Okay. So I discussed earlier this amplifier, right? I gave you an example of this amplifier. Okay. This is your gain of this amplifier is very much dependent on beta. No? It's very much dependent on beta. And you can figure this out by yourself. You try to compute for the delta VI, delta VO, delta VI, and you're going to see that this is very much dependent on beta. So what can you do to make your amplifier more stable? In other words, you want your gain to be more predictable, no? Kasi ganun din, ano? Let's say the temperature increases, so nagbabago yung beta, so biglang nagbabago yung gain natin, o kung hindi masira itong transistor, paltan natin, magbabago yung beta. You don't want that. You don't want that. You want the gain to be predictable. Okay, so the solution is very similar, no, to the current source that I showed earlier. You just put a series resistor. And now you can apply your input directly to the base. Okay, so the gain will not be that dependent on beta. Okay, that's the advantage of this type of amplifier circuit. Do you need an example? Anyway, the advantage of this over this, in terms of it being an amplifier, is you can get much higher gains using this setup. No, in this particular setup, usually your gains are smaller. Okay. I don't think we have to go through an example anymore. No. Although, okay. So let's just do this. No. What would be the input range in which the transistor stays in the active region? Okay, what will be the input range for this particular setup? What would be the input range for which the transistor stays in the active region? Okay, so let me redraw that here. RERC VO VI. Okay, so first of all, the lower range of VI, so VI minimum, will be equal to 0.7 volts. No? So this is on the verge of entering the active region, or the active mode of operation. If your input voltage is less than 0.7 volts, your diode here will never conduct. No? You remember that this diode will only conduct if the open circuit voltage across the diode is greater than or equal to 0.7 volts. No? So yung VI minimum will be equal to 0.7. Now, what is VI maximum? No? VI, so this is minimum, VI maximum. Okay, the voltage here, this is VE. VE is equal to VI minus 0.7. V is equal to VI minus 0.7. No? At VI maximum, this means it's on the verge of saturation. VCE will be equal to VCE sat, which is equal to 0.2. No?